Hi, this is an example problem from chapter 25 about a convex mirror. Pause for a moment to read the question. Alright, so in this problem we've got a convex mirror, we've been told, and we've been given some information, but we are going to be able to use the two equations we always have, mirrors or lenses, mirror in this case, 1 over f equals 1 over do plus 1 over di. And similarly, we've got the magnification equation minus di over do. And in this case, we have a convex mirror. I've already drawn a picture here. So let me go ahead and put my convex mirror in here. There it is. And so this is the front side. That's the reflecting surface. Here's the back over here. And we know some stuff already. So like we know what m is equal to, right? It's positive 0.046. We know where the object is placed, 9.0 centimeters, right? And so we can already put a few things in. Like for the magnification equation, I know that this is going to be, m is going to be 0.046 is equal to minus di over do. Do here, 9 centimeters. And so we should go ahead and check this out real quick just to kind of see what if our sign conventions are right here. So for a converging, for a convex mirror. So convex, we should be getting a focal length that's negative. Expect that. The magnification we could see, it's positive, so that's what we expect. Good. And the image height positive, that means that this is an upright image. Let's go just down and look at the characterization for convex mirrors, since that's what we're dealing with. That's a concave. Way down at the end, convex mirror. Hey, look, all images, doesn't matter where the object is, it's going to be virtual. That means it's going to be on the back. It's going to be upright, and it's going to be diminished. Okay, so that's good to know as well. So in this problem, we've got these various things, and I've got over here, I've got 1 over f. Okay, I don't know what f is. 1 over do. Well, let's see, 1 over do. I know what do is, right? So I guess I could maybe put it over here, right? So I measure from here to there. I'm going to put the object right here. And there's your do. Positive 9.0 centimeters. And so in this problem, it seems like, well, I know what do is, but I don't know what di is yet, but I can solve for it right here from the magnification equation. So sometimes in these type of problems, you've got these two equations. It's okay to have two unknown quantities, di in this case and f, and then we can solve for them both. This one's pretty straightforward because I can go ahead and just solve for di. That's going to be, what do? I multiply by a negative 9 centimeters on both sides. And we're going to end up with this. Minus 9 centimeters multiplied by 0.046. And that gives us a value equal negative 0.0414 centimeters. Now I can go ahead and use this with my mirror equation here. So let's go ahead and just drop this down a little bit. And so we're going to go ahead and do this part now. Solve for the focal length, because what we're trying to figure out is the radius, right? Remember, the radius is related to the focal length. So 1 over f, 1 over do, that is equal to 9 centimeters plus 1 over di, that's this number, and so we get a value here, minus 2.3 per centimeters. And so to calculate F is going to be the reciprocal of this number. We're going to get a value of minus 0.434 centimeters. So there's our F. Now finally we can remember in this problem we're asked to figure out what is the radius of the cornea. So we know that the radius and the frequency are related. For a diverging or for a convex mirror, the frequency, it's equal to minus the radius divided by 2. For a concave, it's positive r over 2. So in this case, we just need to go ahead and solve for r. Multiply by minus 2 on both sides. And that's going to allow us to get our r here. So r is going to be equal to minus 2f. That's a minus 2 times minus 0.434 centimeters, which gives us a value of about 0.87 centimeters. So that's the radius of the cornea in this case, since the cornea is acting as that convex mirror. And knowing the radius allows you to measure the curvature of the eye so that you can get a fitting contact lens. So in general, if you think about it, we can always kind of think of these two equations here as being two equations that share the variables di, do, and so it's always possible, you know, to solve for two unknowns here in these two equations, since we have two equations to do it with.